In the last class, we have talked about self-attention, right? So is that clear to everybody? Are there any questions, or do you want me to recapitulate a little bit? Please respond. Anyway, I cannot see you. At least let me hear you. Dipankar Maiti, are you there? Dipankar, are you there?
Yes, ma'am.
Do you have any questions on the previous classes?
No, ma'am. Just a reading, not fully read till now. So till now, no confusion.
Nikita Singh, you have any queries? Nikita, you're not there? And who is there? Rushali Chakraborty, are you there, Rushali? No, I cannot hear anybody. Ayush Pandit?
Yes, ma'am.
Are you okay with the with the material, or is there any questions?
Actually, ma'am, I haven't yet gone through the slides. Once I read them, I will let you know if I have any doubts.
Yeah, because the reason I'm asking is because today is the last class. Anyway, so as I discussed in the last class, we have talked about the transformer model. So what is the main feature of the transformer model? Ayush, do you remember what is there in the transformer model? Ayush?
No, ma'am, I don't exactly remember. Actually.
You remember what is attention? Ayush? Yes or no?
No, ma'am, sorry.
So who knows what is attention? Pratap Kumar?
Yes, ma'am.
You know what is attention?
Oh, slightly means the attention means probably how to connect with each of the each of the input means in a layer from the output
So to
from
find
the
the
decoder.
representation in a layer from previous data, from previous, from the sequence, right?
Yes.
Now, what type of attention is there in transformer?
In transformer.
Just a minute.
Self-attention.
Self-attention, yes.
Sorry. So transformer is based on attention, right? The main layer of transformer is something called self-attention, where for a particular position in the sequence, you compute its value by potentially looking at all other positions in the sequence and identifying which ones are useful. Based on that, you construct. So, I think many of you have not gone through this. So I will just quickly recapitulate transformers and self-attention. If you have questions, please ask. Don't think that, just before the test, you will read it up. So the transformer model that we discussed, this is the model used by that paper by Vaswani et al. So it has two parts, encoder and decoder. And that encoder is based on self-attention. Based on self-attention, there are several self-attention layers, and every encoder block has self-attention followed by a feed-forward network, which introduces non-linearity. Is it okay? And the encoder blocks can be stacked, and the top encoder block feeds to the decoder. And the decoder also has some type of attention, and the decoder has attention on the previously generated output as well as the sequence in the encoder through the last layer of the encoder. This is the basic components of a transformer: encoder, decoder, and the connection between the encoder and the decoder. So please tell me if you understand. If you don't understand, you said you will read. It defeats the purpose of the class. So as I said, you can have multiple encoder layers in a deep network. For example, in Vaswani's paper, there were 6 encoders which were stacked on top of the other. Similarly, they had 6 decoders. And one possible task which you can do with encoder-decoder architecture is machine translation. For example, this is a sentence in, I don't know, maybe Spanish or Portuguese, and this is a translation of that sentence to English. Now, as I said, in the encoder self-attention, in each block, there is a self-attention block followed by a feed-forward network. And then there are some other these things. For example, there is this sort of residual connections. In the decoder block, there is a self-attention, encoder-decoder attention, and feed-forward network. So if you want to give your input to the transformer, for example, let us take the example of a natural language. You have a sentence. So these are the different words of the sentence. For the words, you have an embedding. Earlier, we talked about word-to-vec embedding, like Sibao or skipgram. Do you remember that? Vaibhav, are you there? Vaibhav, do you remember what is word-to-vec embedding? Varun Madhavan, are you there? Anita Gautam? So I think this is quite frustrating. There are only 59 students in this class. I do not know what happened to the rest of the students. And those who are there, you're not responding. You can say, I don't remember. Or you can say, I did not understand. But don't stay blank. Anyone who is in the class, can you raise your voice?
Ma'am, people are there in the chat. Some people have messaged, I think.
People are there in the chat.
Some people have messaged.
59 people in the meeting. I cannot see my slides, chat, and everything.
Yes, ma'am.
So, can you please respond? Can you say something? No, you're attending online classes. You don't have a working microphone. Is that possible? Most of you are not even in this class. No, this is an elective course. You must understand that. You have taken this course because you want to learn the subject, and I'm trying my best to explain to you. But if you're not there, what is the point of taking this elective? You would have taken another course that you enjoy. Right? So who remembers what?
Ma'am, up to this LS team and all, no, I have followed already. Only the self-attention module, like, could not go through the lecture yesterday.
You did not follow.
Otherwise, word to vector is clearly understood, ma'am.
You know, because my problem is that if I try to teach something based on something that you do not understand, this today's lecture will be in waste, right? If you have not understood self-attention, please tell me, I will explain. But what is the point of, you know, just having the class for the sake of the class and all of you are blank? So Vinod.
Yes, ma'am.
So yeah, self-attention you do not understand, right?
Yeah, no, I could not attend that particular section of the class.
That is the problem, no? If you don't attend the class, if you don't look at the
no, I came a little late. That's the reason. So
there are 60 students in this class. Supposedly on this class, most of whom are not responding. I do not know what happened to the rest of the students.
Ma'am, please repeat self-attention again.
I can repeat, but if people are not attending and they're not listening, what is the point of repeating? I can repeat 10 times, 20 times. I don't have a problem. But I cannot see you. I want to hear you. I want to know that you are there. I don't want to repeat in front of a computer just like that. Otherwise, I'm ready to repeat as many times as you want.
Ma'am, if you could kindly explain this self-attention, it will be very useful.
Well,
yes, briefly, very briefly.
I will explain as long as you wish, but I want to hear your voice. If I don't hear your voice, I will not be able to explain to you.
Yes, ma'am.
So suppose,
hello, ma'am.
Yes.
Yeah.
Can you repeat very beginning today class because I could not attention last 5-10 minutes. So please start again, ma'am.
So I can start again, but I know I cannot start again for people who are not there. So let me explain self-attention. Suppose you have a sequence as input, right? For example, your sequence can be words in a sentence. So x1, x2, xt, xn, right? You can see my board. Can you see?
Yes, ma'am.
So suppose this is a sequence and we do an encoding of the sequence. Let us say we encode this as A1. We encode this as A2. We encode this as AT. We encode this as AN. Okay. Now we are going to have a self-attention layer and we want to compute B1, B2, Bn for the next layer, after the self-attention. Now let us say I look at BT. Now I want to find out what is BT. Now BT is going to be a combination of values of A1, A2, AT, AN in the proportion of alpha Ti AI summation over I. Is this clear to everybody who is in this class?
Yes, ma'am.
So we are going to have BT as a weighted summation of AI. And we want to have higher weight to those positions in the sequence which are important for finding out the contextual representation of BT. Okay. And
alpha Ti is a trainable parameter?
Alpha Ti is a coefficient which we are going to compute. Alpha Ti is the coefficient we are going to compute. We can also generalize it by saying let me just clean it up. So BT equal to, let us say, value of AI. Okay. And alpha TI is how much importance we give to AI. Now, alpha TI is the attention score. Now, I want to ask you, how do we compute alpha TI? What is the principle of alpha TI? So suppose this is the ith input, right? So in order to compute BT, what is your intuition about how much weightage we should give to AI? That is alpha TI. So can you suggest on what basis we can compute alpha TI, which is the importance of AI in computing BT? So please say something and then we
And
can...
the neighboring words will have more weightage.
The neighboring words will have more weightage. That is the principle in convolution kernel. Self-attention is a generalization. We want to understand, neighboring word may have more weightage, or some other word may have more weightage, depending on what we wish. Okay, what is the task? Maybe some other word can have greater weightage also. Okay, suppose...
For example, this I didn't understand. Some other word.
Yeah, for example, let us say that Vinod said that he is going to the market, right? So when 80 is he, when I want to compute BT, now since he refers to Vinod, there should be higher weightage to Vinod rather than he or that, is or that. If your sentence is that Vinod said that he is going to the market, in order to compute the representation of he, perhaps there should be more attention to Vinod.
Yes, ma'am. Yes.
So depending on the task, you will have to understand where you want to put more weightage, right? And that learned value, that computed value is alpha TI. My question is, how is alpha TI computed? So any of you can answer this, or try to answer this. Whether you have followed last class or not, please try to answer this. Isha Sharma?
Is it based on how much the word has to be memorized for the subsequent?
How much the
word? That particular xi has to be, whether it has to be memorized for the following word?
No, we are memorizing everything. The entire sequence A1, A2, AN is there with us, right? When I say alpha TI is how much importance AI has to the representation of BT. Similarly, we can have alpha IN. So which is the importance of AI to BN, right? So a particular word may be important to some position, another word may be important to another position. So we are memorizing all these words, all these the entire sequence. But some of them, maybe Vinod is important for he, going is important for going, maybe Vinod and he are important, right? So for certain words, certain other words are important. Okay, that depends on the task. Now my question is, how do I compute alpha TI, or what is the principle by which we compute alpha TI? What is the basis of the score of alpha TI? You can guess even if you don't remember.
I mean, how far that particular word is away from that?
Yes, far
word?
is one thing that is there in the CNN, but as I said, transformer, has the capability of deciding the importance, not just based on the how far. Because if you want to have the importance based on how far, you could have designed a kernel like that, where the kernel weights are large and the center and smaller as you go far away, right? But we want to give a general framework where the importance need not depend on the distance.
Or it should be based on the word embedding value.
Well, so we have this embedding of A1, A2, AN, and we are going to compute BT. So it depends on the embedding of AI. Yes, and what else? Because the importance of AI to BT and importance of AI to B1, they're different, right? So it has to depend on both AI and BT. Bharatram, is that okay?
Correct, ma'am. Yeah.
So we said BT is my query and AI is my key. So we can compose in general a query corresponding to BT and a key corresponding to AI. So Q and K are two functions, and we can take a dot product of these two. So Q of BT gives me a vector, K of AI also gives me a vector. These vectors have same dimension, let us say D, and taking the dot product, we can find the score alpha Ti. So like this, we can find alpha T1, alpha T2, alpha Tn. Okay. Now, these values are general values. We want to normalize the values so that their sum is 1. And for normalizing, we use the softmax function to get the actual alpha Ti. Is this clear? So alpha Ti depends on some notion of similarity between, we don't have BT actually, this is query of AT. We only have AT now. So it is based on query of AT and key of AI. Is this now clear to everybody?
Yes, ma'am.
Everybody, is it clear?
Yes, ma'am. Yes, ma'am.
Don't say that, I don't know today, the day before the test, I will read. Because if you don't understand, I cannot proceed with the class, right? So this is what alpha Ti. So based on this, we can compute BT, and we can do this for B1, B2, Bn. So this sort of computation is called self-attention. Is this clear?
Yes, ma'am.
Yes, ma'am.
How do I end this? Yeah, so coming back to this, in an encoder, we have a self-attention layer. Suppose this is a layer. So we have initially the input X. We have the input X. From that we get A. And then we have self-attention followed by a feed-forward network to get B. So we can say that this is A and this is, let us say, H1. And then we can have another encoder layer to give me H2, H3, etc. Why do we have the feed-forward layer in between the self-attention layers? What is the role of the feed-forward network layer? What if we remove the feed-forward network and only had multiple attention layers?
Ma'am, temporal. No.
Temporal actually is a very important thing. And how do we incorporate the temporal position? What we do is that from X1, we have an encoding of X1, and with that we add the position of X1. So we have a positional encoding of that position. That position of actually X1 is position 1. So position of 1, there's an encoding. By adding that, we incorporate the positional information. But that is not the answer to what I asked. Why do we not have pure self-attention layers? Like you can have pure convolution layers. Why do we add something after the self-attention layer?
Then the sequence of the input is not detected if we use only self-attention.
No, so to detect the sequence, we add positional information. That is a separate concept.
Okay, so if we use on
features itself, because if we don't have a feed-forward layer, how can we extract the features from our input?
No, self-attention itself gives you the features. Basically, this feed-forward layer is used to incorporate non-linearity. This self-attention mechanism is just a summation, right? It's a linear sum.
Yes, ma'am. Linear combination it is.
It's a linear combination. If you have multiple self-attention layer, you only get a linear function, which does not have, is not a powerful function. So by introducing some nonlinear activation like the sigmoid, etc., we can make sure that the deep neural network can learn complex functions. Is it okay? Is it clear to everybody?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
So that is why we have the feed-forward layer. So we have positional information which is encoded. We have fixed positional encoding based on a combination of sinusoidal and cosinusoidal function, or we can learn the position vector for a position t. Okay, and that is added to the encoding of the input to get my first input to the encoder, first encoder. Then each encoder block has self-attention followed by a feed-forward network. There are some other tricks. For example, there are some residual connections. There are some normalizations and so on. There are also multiple heads so that it acts like multiple kernels so that they can focus on different components, etc. A decoder has 3 blocks. Apart from self-attention and feed-forward, in the middle it has another block which is encoder-decoder attention, where for a decoder state L, suppose SL is a decoder state, we want to find the attention on the ith encoder state. So SL and AI, based on some similarity.
Ma'am, isn't it a strange way to concatenate or add up positional embeddings and input embeddings together? Because wouldn't it be better if we have separate self-attention blocks for these two separately instead of simply adding them up and passing it to the network for it to decide?
No, sir. You see, wait, there are 2 questions. One is, why are we adding them? Right? We could have added them, we could have concatenated them. People have tried both. But I did not understand your other part of the question. You said separate self-attention blocks. I did not understand. Self-attention is one block which looks at the entire sequence and computes the entire sequence at the next layer, right? Because DT is computed based on all, potentially can look at everything in the previous input, we cannot have a separate self-attention block. I did not understand your question.
I understand, ma'am. Yes, I get it. I understand. What I'm asking is, supposing our input embedding is input vector is something like a 1D array, n of size n. So we don't usually add up all the n elements and pass a single element. We have separate n elements
We
to
are
represent
not passing
features.
a single element. A1 is a vector. An is a vector. So we have a sequence of vectors, right? Suppose in NLP, suppose we have W1 is a word. So we have a word vector, okay? And then for position 1, we have the position P1 vector. Then we have W2 vector and we have P2 vector. We have Wn vector and n vector. So position 1 is vector for the position 1, vector for position 2. Those we are learning. These two are added to get A1. So embedding of W1 plus position vector of position 1 are added to get A1.
Okay.
Okay. So this positional information intuitively helps you to keep track of the sequentiality in a roundabout way. And because this vector is learned, it may learn, and their absolute values are learned. For one, you pick that, suppose my maximum sequence size is 100, I'm going to learn the vectors of 1 to 100. But the learning happens in such a way, because sometimes the relative position is important for different tasks, the learning can take care of that. Is this okay?
Yes, ma'am, it's fine. Thank you.
The third thing which I also mentioned is that just like CNN can have more than one kernel, transformers can have multiple heads. So corresponding to a head, what are the parameters? Suppose you have a single head, and we saw that in self-attention, we find the query of AT times T of AL, which gives you alpha TL, right? So what are the parameters that are required in attention for self-attention?
Key query value.
Right. So here, where are the parameters? In this function, which are the parameters?
Word encodings.
These are the parameters of this function. So Q is some function, and that function can have parameters, right? If you have a single head, you may not have any parameters. You can just say t.ak. If Q is an identity function, there is no parameter. But in general, there are some parameters, and the parameters are the parameters of this function based on how you define the function. So in the first model, how they have defined this function is they have learned a matrix WQ, a matrix WK, and another matrix WV. So this matrix has certain parameters. So QAT is WK multiplied by AT. And key of AK is WK multiplied by AK. Okay. So WQ and WK, sorry, this is WQ. WQ and WK and also WV, these are the parameters of the model. Is this okay to everybody?
Ma'am, can you please once again repeat this WV?
First, let us look at WQ and WK. WQ is how we get from a component to the corresponding query, and WK by multiplying AI with WK into AI gives me the key of AI, and WQ into AI gives me the query of AI. Is this okay with you?
Yes, ma'am.
Now, we can also have another this thing. Wait. So we are going to find out, we say we are going to find out BT by finding out summation of alpha Ti, I equal to 1 to n times value of AI. So what is value of AI? This is in general an arbitrary function, but in the transformer model, they used a matrix QV. And QV multiplied by AI gives me the value of AI.
Ma'am, we are just converting the input to a variable that is Vi.
Yes.
Okay.
So you know, in AI, either I can take AI as it is, the value can be an identity function where I just take the summation of the previous inputs, or in general, we can have a transformation. So for corresponding to each AI, I can find its query vector, key vector, value vector, right?
Yes, ma'am. Understood.
And this is what we can use. And the reason we need to do it, one of the reasons we need to do it is that if we have multiple heads, then for each head, we have different query key and value vectors. Otherwise, we will not be able to have multiple heads. So we can have, let's say, 8 heads in the original transformer, and we have 8 sets of Q, K, and V vectors. So we can have this, sorry, matrix, so Q, K1, V1, Q2, K2, V2, and Q8, A8, V8. Right? So these matrices, each of them, its set corresponds to one head. And these multiple heads we get at the next layer. Instead of B1, we get B11, B12, B18. And we can add them to get B1 and then normalize it. Is this okay? Any questions, please ask.
No.
So more specifically, this is the encoder block. We have the input. This is the input embedding after taking the embedding plus incorporating the function encoder. This is the self-attention embedding. This is a residual connection. Then they're added and normalized, add for the multiple heads and also add with the original input through the skip connection and then normalize the values. Then it goes through the feed forward network and then again add and normalize one more residual connection. This is the full encoder block. Similarly, in the decoder block is similar, except that we have an additional component, which is the encoder-decoder attention. And then in the full transformer architecture, you have multiple encoder layers stacked, and from the last encoder layer feeds to the decoder and multiple decoder layers. And at the end of the topmost decoder layer, you can get the output. And for the output, suppose your output, you want to output a sentence, which is a translation. So each output is a word, is a classification task. So in the output, the last layer is a linear layer followed by softmax. So you can take softmax over all the classes. In this case, over all words in the vocabulary. Okay? So you get a probability distribution of all the words, and then you can use either greedy decoding or beam search decoding in order to get the answer. Is this clear? So with this background, which is a transformer model, I spent almost all the class today. Now see how the BERT.
And this self-attention layer.
Actually, there is some noise. If you are not talking, please mute your microphone. Yeah. So what was the question?
Ma'am, my question is, if this self-attention layer, we can insert it in a CNN layer also, right?
You can repeat your question in the
I mean, in a CNN network also we can use the self-attention, right? Not only in LST, right?
No, can you repeat in the CNN? You can do.
No, after a CNN layer, can I put a self-attention layer?
Yes, you could. So there is no LSTM here. This is only a self-attention layer. We have self-attention.
Okay. Any encoder we can use it, whether it is a CNN-based encoder or
actually, this self-attention is based on neither CNN nor RNN or LSTM. Just separate thing.
Okay.
Self-attention is not based on RNN, not, it has some similarity
with
RNN.
It's based on some input function.
It is something different.
Okay.
What is a CNN layer? A CNN layer, if you have the inputs x1, x2, then, right? So suppose we call it A1, A2. In order to you are going to look at 80 minus 1, 80 plus 1. This is what a CNN does. Okay. So what does self-attention is an alternate to CNN, where you are going, and CNN, the kernel has fixed weights. These weights are not. So in a self-attention, on the other hand, BT can get constructed out of this entire sequence, right? And these weights, individual weights are not learned, but the parameters WQ, WV is learned, and through similarity, you can find the weights. So in CNN, the kernel looks at a fixed size kernel. In self-attention to compute BT, you look at the entire sequence, and the sequence can be of any length. You do not put any constraint on the length of the sequence. Sequence can have a length 5 or 50 or 500 or 700 or so on. Okay. So self-attention is a concept which has some similarity with CNN, but it is a different concept. Is it clear?
Yes, ma'am. Yes, ma'am.
And it is different from RNN. So it is somewhat more similar to CNN in that way because it is done in parallel. It is different from RNN. RNN, you have the sequential connections. Is this clear?
Yeah, why I asked this question was because I have seen in some CNN-based architectures, they have used the self-attention after some CNN layers.
Yes, actually all these concepts can be combined into some.
For example, in unit, in some modified unit architecture, yeah, they have combined self-attention with the.
No, I understand. We are trying to tell you what are the basic architectures. Now, all these concepts can be combined into an architecture that you use. So you should be aware of the individual architectures, right? So you can combine, these things in different ways. Is that okay? So the convolution
yes,
is one concept. Self-attention is one concept, right? You may have a deep learning system where these concepts are combined. But this self-attention is neither RNN nor CNN. It's something different. It has some similarities with both, but it is a different architecture. I mean, different module. Now, we are going to talk about, using transformer, how to find the representation of a word. Earlier, we have done word to vec. We want to improve upon it. So this is something that I have talked before, but I'm just trying to repeat it. So in deep learning, we often come across transfer learning. So what is transfer learning? You train your system on one task, right? And you take the trained model and then adapt it to a second task. So the some pattern that you learn from task 1 can be used in task 2. In particular, when you want to learn representations of text, I mean, I'm talking about text, it could be anything else, or you want to learn the embedding, then as we saw in word to vec, and as we will see now, we can leverage unlabeled data to cut down on the number of labeled examples. We also introduced this term called self-supervised learning, where given the unlabeled text or unlabeled data, we can construct some supervised instances based on the language modeling task, and based on that, we can learn the representation. So we can take, because large corpus are available today, we can take very large corpus, which is unlabeled billion word corpus, and from that we can learn representation, which we can use in other NLP tasks. And this is shown in the schematic diagram here. You have unlabeled text, and you take huge quantities of this unlabeled text, and from this you learn a self-supervised model to represent words or words in their context. This is called unsupervised pre-training. And then you use this model. Suppose your specific task is sentiment classification, and suppose you have some movie review data which are labeled, and you fine tune on that task to get a sentiment specialized model. So this step 2 is called supervised fine tuning. Because of unsupervised pre-training, it is possible that with fewer amount of labeled data, you can still do well on task 2. Is this okay? Now coming back to word representation, we have talked about word embedding, where each word is constructed, is converted to a vector in some d-dimensional space. Right? So this was on-hot encoding. This is word embedding, and in the word embedding, which is learned by using distributional hypothesis, it's different from classification, but it can put similar words together, and it can also capture certain relationship between the words. However, this sort of word embedding has some limitation. We have discussed that in natural language, a same word, say bank or play, they can have a table or book, they can have different meanings in different contexts. Word embedding learns a single embedding for every word. And the solution is to learn a contextual embedding. So for example, in this sentence, there's play, let's play baseball, where play is a verb. And here we see, I saw a play yesterday where play is a noun. So these two play have different meanings. And in this case, even different part of speech tag, but in word to vec, they will have the same embedding. So the idea here is that when we learn the embedding of a word, we learn the embedding in the context of its use in the sentence or the text. Okay. So one naive possibility is that you have a language model based on RNN or LSTM or bidirectional LSTM, etc. And then you take this output as of this language model. This can be a unidirectional language model or even a bidirectional language model. So this gives you the representation of word in its current context. So we want to explore contextual representation of a word. Is this okay?
Yes, ma'am.
So this is another example. Suppose this word bank is used in 3 different contexts, and we want that the representation that we get should be different for these 3 contexts. So typical language models like RNN or GPT that we will see, they use either left context or right context. But if you want to say that the meaning of a word comes from its context both at the left or right, you can use a bidirectional model. If you want to use a language model for generating, right? If you want to generate text, then you have to use a unidirectional model because you can only do the generation based on what has been generated so far. But if you use a language model for representation, you can look at bidirectional context. And one of the initial bidirectional contextual embedding was Elmo from Facebook. So Elmo comprises of several layers of bidirectional LSTM. So this is one bidirectional LSTM where you have one RNN or one LSTM going from left to right, another going from right to left. And based on that, you find out the representation from the left to right LSTM and the right to left LSTM. You concatenate them to get the representation which takes care of context in both the directions. So Elmo is one of the language models that comprises of layers of bidirectional LSTMs that provides a contextual representation. In fact, Elmo has multiple such layers, and all these layers are combined in order to get the final representation. So Elmo became a very useful model when it was introduced. So Elmo, to summarize, is a bidirectional LSTM model, train forward and backward language models, and use the concatenated LSTM states to represent the word. So Elmo was based on bidirectional LSTM. Next came BERT, which is also a contextual representation, but it was based on transformer language model. Now, so BERT is a deep bidirectional language representation pre-trained using an unlabeled text corpus. So among pre-trained representations, there have been a lot of work. For example, context-free, what we have discussed is word2vec. There's also GLOVE, which I did not discuss. For contextual, there are unidirectional models like GPT, which I will talk about soon. And there are bidirectional models such as Elmo and BERT. So this gives us the schematic diagram architecture of these models. So BERT, takes a sentence or takes a sequence of text as input and comes up with representation of each of the positions in the context, in the current context. Okay? And the self-attention networks, there's a connection from each unit at a particular layer to every other unit in the previous layer. And BERT is based on the transformer self-attention model. In particular, BERT is the encoder part of transformer. Another language model that was being developed by OpenAI, again based on the transformer, is the GPT model. GPT model is useful for generating, and it is also a transformer, but it has only left to right connection. And this is similar to the decoder of transformer, where by masking, we can mask the future positions. And the ELMO, as I have already described, is based on bidirectional LST. Any questions?
Ma'am, GPT, can you please repeat?
GPT I will talk about.
Okay.
So yeah, I'll just repeat. GPT only contains left to right connections. It masks, so if you look at position 2, it doesn't have connections from 3, 4, 5, 6, etc. It only has connections from 2 and 1. At position T, you have connection from 1 to T minus 1. Is it okay?
I'm not fully understood.
No, you will understand.
Okay.
In a transformer encoder, the next representation layer is based on the previous representation layer.
Yes, ma'am.
And looks at all positions in the previous layer.
Yes, ma'am.
Okay. Now GPT is used for generation. Okay. So when you have the TF, you want to generate BT. BT is based on A1, A2, AT minus 1. Why? Because so far we only have A1, A2, AT minus 1. AT plus 1 have not been generated yet.
Oh, yes, ma'am. So it generates 80 and 80 plus 1.
GPT is used for generation, right? You generate one word at a time, just like the decoder of transformer.
Yes, ma'am.
GPT is used for generation. I mean, ideally, both can be used for both purposes in a convoluted way, but typically GPT is good for generation tasks, such as machine translation, summarization, text generation. And BERT is useful for representation. And the entire sequence is already available to you. Is this clear?
I have one question.
Yes, ma'am.
Yeah.
Ma'am, I have one question. Hello?
Yes, please ask.
So, ma'am, when we did word to vec, one of the things that was taught about was that the whole idea of word to vec was a context, like an apple, usage of an apple as a fruit, and an orange as a fruit had a context.
Yes. From the context, we get the representation.
Correct.
But we learn the representation per word and we store that representation. Right? So
that is true, which is why we were able to plot it also in a certain dimensional space, and we could see similarity of words and clusters.
Okay, but suppose we take the word play, suppose it has 5 different senses, 5 different meanings, but we have only one vector for play, which takes into account all the context of the word play.
Correct.
Okay, so you have a unique, the word to vec is computed based on the context of a word, of the different contexts of the word in the training corpus. Right?
Correct.
Now, when you are during your use, when you encounter a word in a particular sentence, now you are only looking at the global vector for that word. But I want that in this sentence, in the current sentence, what is the representation that I should look at?
I see. Okay.
So yes, word to vec is based on the context. Everything is based on the context, but we only store one vector per word, and that vector we use. Whereas
that is correct.
In BERT, for every word I don't get a vector. BERT does not give a vector per word. What BERT gives us is a model. Suppose it is a model of depth 6, right? So BERT gives us the model with the parameters of the model. BERT does not tell you this word is going to be represented as this. So BERT gives you a model. You put your words, suppose you have a sentence. you use word2vec of each of the words, you feed it to the model, and then at the final layer of the model, you get the output. So if you have the word play here, the final layer of the BERT, you will compute the contextual representation of the word play.
Okay.
BERT gives you a mechanism to compute the contextual representation of a word. Word2vec, for every word, computes a fixed word vector and stores it.
Got it. Yep.
Is it clear?
Yep, absolutely. Thank you, ma'am.
So, BERT is essentially the encoder part of a transformer. Now, the question is, how is BERT model obtained? How is it trained? Right? So, we are going to use our corpus. From the corpus, we are going to use different, text, maybe all the sentences, or, however we break the text, we are going to use the textual input. And now we have to train BERT on some task. And what is the training that we do? We randomly choose some of the words and mask those words, right? Suppose we had, W1, W2, Wn, this is my sentence. So I say that's 5th position I mask. 11th position I mask. So the word 5 and word 11 are replaced by the word mask or a special symbol. Rest of the word I keep as it is. And the objective, the ideal target output is the actual sentence with the actual words for the masked word. For example, suppose you take the sentence, I think before I am, and you choose to mask the 2nd position and the 5th position. So you give input to BERT, I mask, therefore I mask, and the desired output is I think before I am. Therefore I am. So basically, you will check if think and am are being output correctly. Is this clear? Have you understood how masking helps us to generate the training instances?
Yes, ma'am.
Okay. So randomly you mask some input token, and then you can use the remaining things both from the left and the right to try to predict that word which you have removed. So in fact, there are two things used for training BERT. One is the most important component is the masked language model, which I just explained. You take the input and you randomly pick some positions which you mask. In the BERT paper, this was a paper by Devlin et al. In 2017, I think. So in Devlin's paper, they chose randomly 15% of the tokens to mask. Okay. And the objective is the output of BERT is the correct words. And you evaluate it based on whether the masked word was predicted correctly.
Ma'am, why are we taking 15% of the tokens? Is this a rule?
This is an empirical value used in Devlin's paper.
So we can change it based on the context in which we are
Yes,
using.
you can change it and experiment it with. Maybe Devlin and all did a few experiments and they chose 15, right? Like most of machine learning and deep learning, this is just empirical.
Yes, ma'am.
Now, the second objective that they put in BERT is the task of next sentence prediction. So the idea is that you, from your corpus, you take two consecutive sentences, ST and ST plus 1, right? So you can say ST plus 1 follows ST. But if you take, let us say S5 and S21, so they are not consecutive. So S5 and S6 are consecutive. So S5 and S6 are consecutive sentences. S5 and S21 are non-consecutive sentences. So you pick, pairs of sentences. 50% of the pairs are consecutive sentences. 50% of the pair are non-consecutive sentences. And you want to train BERT to understand, to tell whether that pair is consecutive or not. So this is how you feed the input. In the first position, this is reserved for class, so you don't give the input. Then second to whatever is the length of the sentence, you give the first sentence in the pair. Then you put a special symbol called, these are special symbols called the separator symbol. Then you give sentence 2. This is the input to BERT. And the output to the BERT, you ignore the other output. The first position in BERT corresponding to CLS. So at this output, you want to predict yes or no. So this is a binary classification problem. So you can have a linear binary classifier, maybe a linear thing followed by a sigmoid unit, where you try to predict yes or no, 0 or 1, or the probability that it is a pair, consecutive pair. Right? Or to generate non-consecutive pairs, you can say S5 and S6 are consecutive. S6 and S5 is not consecutive. Or you can even say S6 and S21 are not consecutive. Okay? So you generate positive examples of consecutive sentences and negative examples of consecutive sentences, and to train BERT to learn this. So both this task, masked language model and the next sentence prediction, both these are used for training BERT. Is this clear? Any question?
Ma'am, the masked model seemed intuitive. This one is a bit non-intuitive. How is this consecutive sentences helping it to learn the context of?
Let me answer. There are certain modern, versions of BERT. They only use the mask for training. Okay? But for this particular, actually, whether this is useful or not depends on how big the corpus, how big the model, etc. So Devlin's paper found this to be useful. But beyond whether you can learn, there are 2 tasks that have been defined. One is the masked language model task, other is the next sentence prediction task. Now, in some of the other models, people have only used the masked task. However, I want to tell you that there is a reason for using this approach, because when we use BERT, we will use BERT in different types of NLP applications. Many NLP applications require 2 segments of text. For example, machine translation. For example, summarization. For example, question answering. Right? And if you want to use BERT for those tasks, this sort of notation is useful. For example, you can give as input for question answering, you can give the CLS symbol, then the question sentence. The question sentence, then the separator symbol, and then the answer sentence. And you can ask, is this the answer of the question? Okay? So if after the question sentence you give another random sentence which is not the answer, you expect BERT to say 1 if the answer is an answer to the question, 0 otherwise. Okay. So this sort of use of BERT is very common. Does this
Understood.
answer
Interesting. Yeah. No, I think it does. Interesting usage, but quite a intelligent use.
That is a very common usage. You use BERT for many tasks like this, which involve pair of sentences. And the BERT architecture has to support those tasks. Now, when BERT was proposed, they showed that a large number, almost all of NLP tasks, benchmark tasks, by simply applying BERT and doing nothing else, almost nothing else, we were able to beat the previous state-of-the-art methods.
Yeah.
To some, yeah. Any observation?
No, I think definitely. And now that I think of harder, I think yeah, the sequence also does make sense. You know, if you're talking about a bank, perhaps the next sentence is going to talk about something with credits and interest. So there is definitely a context that does gather in consecutive sentences versus otherwise.
Actually, it depends on how BERT is used. BERT is not just used for language. If it is only used for fill in the blank, you remove a word, predict it, then the first would have been okay. But you also want to use for many tasks which involve two types of text. And we will see some examples. But first we summarize. So BERT, what it does is that you can give your initial sentence as input, and BERT can have multiple layers, and you get finally the representation of the sentence where, for suppose this is word I, this gives you the contextual representation of word I. Okay. And this you can use for further things, or you can directly get the output. We'll show some examples. So BERT is basically only the encoder part of the transformer. And BERT stands for bidirectional encoder representations from transformers. Okay. So now we get into a little more detail about how the BERT input is given and how the output is used for certain tasks. So in general, BERT allows you to input up one sentence or a pair of sentences. There are both use cases. In some case, you want to give only one sentence as input. In some cases, you want to give a pair of sentences as input. And in this case, with that, you use a separator. Right? If you have a pair of sentences, you have a separator. Also, BERT uses subword representation, which I will explain. Typically, the naive way to do it is if you have a text, you tokenize it into word, and every word has a representation. But if you take a very large corpus, the number of unique words can be very large, maybe several hundreds of thousands, right? And a large number, almost half of those words are rare words. You might have found them only once in the corpus. If you want to represent each word, the total size of the vocabulary becomes extremely large. Okay. So instead of representing one word, as a token, one token as one input, BERT finds a clever way to find subwords so that you can have a limited number of subwords. Suppose you say that I want only 30,000 as my vocabulary size. Okay. Now, the smallest vocabulary size you could have is 26, let us say. If you ignore punctuation, you can say A, B, C, D, Z. If you're dealing with English, you can say my vocabulary size is 26 and maybe blank and a few punctuations. And any other word you can compose by combining characters. Or maybe you can have, one token as not, one word piece as sentence, another word piece as E, another as S. By combining these three, you can get sentences. So you can keep each individual character as a word piece or a subword, and you can have some longer subwords, and so that the total number of subwords is less than your budget. Suppose you want 30,000 subwords, you make sure that you have exactly 30,000 subwords, so that any other word can be composed by concatenating these subwords. So we'll discuss this. So BERT uses subword representation. Now, suppose, based on word or subword, you can get the initial tokens. Now, when you embed the token using word2vec or something, first you have the embedding of the symbol CLS. Then you have the embedding of the first word, second word, third word, fourth word. If you are using a pair of sentences, then you give a special symbol called sep, and then the words in the second sentence, followed by another separator. Okay. Now, as we have discussed for a transformer, you also have a positional embedding. This embeds 0, this embeds 1, this embeds 2, etc. So you add this subword embedding with the positional embedding. There's a second thing that we require when we are dealing with a pair of sentences. We want to know whether the current position belongs to the first segment or second segment. So you have two segments, EA and EB, and you learn the embedding of these segments. So to this, you add the subword embedding of the segment to which this word belongs, and the position embedding for this position. So these three are combined to find the input embedding. Have you understood?
Yes, ma'am. And this positional embedding, this is what we earlier discussed regarding temporal.
Yes, earlier we discussed, yes.
Yes, ma'am.
But for the two sentence task, we also have a segment. Using similar method, we can learn the segment embedding. Now, let me talk a little bit about subword tokenization. Okay. Both BERT, which was developed from Google Labs, and GPT, which was developed by OpenAI, they use some sort of subwords. So BERT uses word piece, GPT uses byte vector. So they're two different things, but both of them achieve subwords.
Ma'am, Bharat here.
Yeah.
One quick question, ma'am. This BERT, it's a pre-trained model, right? So we have different types
Yes.
of pre-trained model based on cased, uncased, and based on different vocabularies, which means that we already have certain word vector representations of the different words in the model. Okay, so today, let's say I'm getting a new set of words and I'm trying to train it. Is it like I just have to pick up the word vector?
Wait, I did not understand. Let me clarify.
Yeah.
You have got a very large corpus for a language, right?
Correct.
From the very large corpus, you try to learn the parameters of the BERT model.
Okay. No, my question, I may be wrong, because what I understand is it's a pre-trained model wherein you already have word vector representation of different words.
No, word vector is separate. The BERT model comprises of the values of the parameters of BERT.
Okay.
The word vector which we are taking as input, if you are thinking of this line, this embedding is an embedding which can be done separately. For example, by using word2vec.
Correct. So my question is, what is that advantage that I'm getting if I'm using a pre-trained model like BERT compared to me training my entire corpus and then getting the representation?
No, the advantage, as I said, let me say that, suppose you have a task called question answering and you have got 1,000 questions and their corresponding answers. Right? You have got 1,000 questions and 1,000 answers.
Correct.
Now, if you apply a supervised model in these 1,000 questions and 1,000 answers, the model will be too small. It will not be able to learn.
Correct, because the corpus is less.
What we are using for BERT, we are using a billion word corpus, from which we are learning a pre-trained representation which captures a lot of knowledge which is already there in the corpus. And we use this model as a starting point, this model. And then with this 1,000 new examples for the question answering problem, we fine tune the parameters.
Okay.
So if we did not use pre-trained model, BERT or not, if we did not use pre-trained model, to be able to do a task well, we will require a huge question answering corpus. And it is very difficult to get a question answering corpus.
Correct.
It is easy to get a large amount of unlabeled text.
Okay.
Right? So the advantage of any pre-trained model like this is that during pre-training, you have learned captured a lot of knowledge from that big corpus. Right? And this knowledge is your background knowledge. Now you bring in that knowledge, and with a few examples of the new task, you are able to do well on that task.
Okay.
Does that answer your question?
Okay. Okay. I mean, it kind of answers, but my only thing.
Why is it kind of?
My doubt is, see, we get word embeddings out of the BERT model. Okay, let's say I pass in different words and I get a word embedding out of a BERT model. And the same.
I don't get a BERT embedding. I don't like the word embedding. I get the BERT model. So the BERT model, there are different parameters in the different layers. For example, for the self-attention layers, we have the WQ, WK, WV for each attention head. So we have multiple self-attention layers. We have a feed-forward network where also there are some parameters. So BERT model is a model which comprises of the values of these parameters.
Okay. Okay.
Right? Like you use CNN for transfer learning. You learn a CNN on ImageNet, you chop off the last layer and you take it and you apply it to another task.
Correct.
So BERT is a model.
Okay. It's like a dictionary from which
get an embedding.
Understood.
Is it okay?
Yeah.
The embedding is here only used here. This is a fixed embedding of the words or the tokens which are used here.
Okay.
Now, what are these tokens? As I said, instead of using every word as a separate token, BERT uses word piece tokenization. So the idea is now, suppose you developed the embedding of 100,000 words. Those were the unique words in your vocabulary, in your corpus, right? Now, when you apply it, you get a new name. Suppose Bharatram happened to be not there in the million word corpus. Now for Bharatram, we will not have any embedding.
Correct.
Right? So that model will fail.
Correct.
So, but if we have small subwords, including all the characters, even if Bharatram is not there, I can construct Bharatram from B plus H plus A plus R, etc.
Correct. Correct.
So, first, we take all the characters, say 26 plus punctuation or whatever, so 30, 40 characters, we start with that. Make sure that any word can be constructed. Now, suppose my budget is 30,000 tokens. Suppose it can be 10,000, 50,000, whatever. So now we still have more tokens, more word pieces that we can construct. So we have a target vocabulary size, right? So while vocabulary size is below the target size, we build a unigram language model. What is a unigram language model? For every word, we find its count. Okay? From my large corpus, I say Bharatram has occurred 2 times. The word the has occurred billion times. Vinod has occurred 500 times. So for every word, I take its frequency. Now, I merge 2 of my pieces that leads to highest improvement in language model perplexity. Just a minute, I have a call. Hello? Hello. Sorry about it. So now a language model is a task of predicting the next word, right? For predicting a word which you have removed from the context. Now, when you develop a language model, you want to, suppose you want to predict a word and you can evaluate it, right? And one of the evaluation measures is called perplexity. Okay, I will not go into the details of this evaluation measure. This is a simple evaluation measure to see that basically you want to, the low perplexity means the likelihood of actual text is higher, right? Suppose you have a corpus comprising of some sentences. You want to learn a language model so that these sentences will have higher probability, the sentences which are actually there in the corpus. And perplexity is a measure which is related to this likelihood in a somewhat inverse manner. So anyway, so we want to merge two pieces into one piece, one additional piece. Suppose you have A, B, C, D, Z to start with. Suppose I said merge B and E. You keep B, E separately, also add this new token B, E, so that the resulting perplexity is improved. Okay. So now initially, suppose I had 30 tokens. When I add B, E, I get 31 tokens. I again take two word pieces to merge. Like that, I keep on increasing the number of tokens till I reach 30,000. Is this clear? So this is a method of constructing subwords. And why subwords? Subwords are useful because from subwords, you can even construct unseen words. And because many words are very rare in the actual corpus, instead of trying to keep the representations embedding of those words, you only keep the representations of the subwords. When I talk about representation, I only mean for this layer, right? Where word-to-vec type of embedding can be used. So this is the concept of subword tokenization, and the particular method used by BERT is called word piece. Is this clear? Any questions?
No one.
So BERT uses some variant of the word piece model, and based on this word piece model, the words which are relatively common, whose frequency will higher, will be there as full words in the vocabulary, but some words will not be there. For example, this word hypatia, which is quite rare, which may not be there in the vocabulary, but you can construct it by concatenating some of the word pieces. For example, suppose you have the word piece H, YP, ATI, A. By concatenating them, you can get hypatia. And because you have the individual characters in the model, you are ensured that any word can be constructed. So how is the word piece model obtained? You are given a training corpus, large training corpus, and the number of desired tokens. You tell whether you want 10,000 tokens or 30,000 tokens, etc. So you want to select D word pieces such that the resulting corpus is minimal in the number of word pieces when segmented according to the chosen word piece model. So let's forget it. But basically some optimization that we are trying to do in optimizing the word pieces that we have. And that is based on the heuristics that we discussed in the previous slide. Is this clear? Now we have all pieces of the BERT in place. And this is what we have already seen. This is how BERT looked like. Just repeating, you mask out, this K is a hyperparameter. You mask out K% of the input word. In the original paper, even in Devlin's paper, they use K equal to 15%, which is the same which was used. So the 15% they have used, but you can look at other values. And there are pros and cons of making this value bigger or smaller. And an example, suppose you have this sentence, the man went to the market to buy a gallon of milk. So you mask this word, and you desire that your model should be able to predict the correct word. If you have too little masking, that is k is smaller, then you will get it will take more time to train because you will get less number of examples. If you have too much masking, the context will be lost because a lot of words in the context will be masks. So there is a trade-off. Now, there are certain problems with this masked language model because the mask token that is not seen while you are fine-tuning. So there are some, some tricks that people have used. So what actually is done in that paper is that you choose 15% of the words to be predicted, but do not replace all of them with mask. Out of the words that you have chosen, 80% of the time they are replaced with mask, 10% of the time they are replaced with a random word, 10% of the time the same word is kept. For example, if the sentence was John visited Madagascar yesterday, given this sentence as input, this position Madagascar should be predicted. But when you are generating the input, 80% of the time corresponding to this position you put mask, 10% of the time you just pick some random word of John, keep, time, anything, and 10% of the time you keep the exact similar. So this is what the paper used, and this enabled this model to perform in a better way. This next sentence prediction task I've already discussed. Now, so BERT can be used in many ways. Suppose you give a sentence, you can say, this is my encoding of the sentence. My dog is cute, he likes, etc. So you want the representation of the contextual words in the sentence, or you want one vector to represent the entire sentence. If you want one vector to represent the sentence, or if you want one class to tell what is the topic of this sentence, in those cases, you can use the first position corresponding to CLS. Okay, so this position, the first position is always kept reserved in the input for CLS, and this position can be used for a task which requires a single output. It could be a sentence representation task, it could be a classification task, it could be some numerical task, and so on. Now, as I said, if you want to apply BERT, you take the pre-trained model of BERT as the first layer of your final model. And you can train, if you have a little amount of data, some amount of data in your chosen task, you can fine tune the model with that data. And these are some standard parameters for fine tuning that people have used empirically. So let's see some examples. Suppose you do sentiment classification, sentiment analysis. You want to tell, given a sentence, is the sentiment positive, negative, or neutral? Okay? Or given a document, you have 10 classes, you want to classify the document in one of the 10 classes. How do you use BERT? You give the input of the sentence. In the first position, you give the CLS symbol, then W1, W2, W3, or corresponding to the sentence, you find the word pieces and their embedding, positional embedding, etc. So this is how you construct the input. And then at the output, you ignore these outputs. You only take the first output, and then you pass it through a simple classifier, which will tell you the class. So the parameters of this linear classifier are trained from scratch. And the BERT model, the pre-trained model, was taken by you, and you can fine-tune the weights of these parameters based on your limited training data. Is this clear? How you use BERT for classification? Any questions?
No, ma'am.
Is it clear? Kaustubh, is it clear?
Yes, ma'am.
So as I have said, that you give as input the CLS token and the tokens. Then you have the full BERT model, and you only take the first output, and from that you try to get the class level. A second example is, suppose you have a case where you want to give the part of speech of every word. You give a sentence, so you want to give the part of speech of each word. So you feed the sentence as CLS W1, W2, W3, and in the output you ignore the first position, and in the other positions you can get the class. Another example is in semantic slot filling, where you are given the sentence, for example, arrived Taipei on November 2nd, and for each word you want to find its role. Like arrive is other, no role. Taipei is destination, on is other, November is time, 2nd is time. So here for every input position, you have an output for the class, and for that you can have a simple neural network or simple linear classifier to give you the class, and this position you can use. Is this okay?
Yes, ma'am.
So, named entity tagging is another such example, that could be done with the previous one. Now let us come to our example with question answering. Okay, so you have CLS as input, then you have the tokens of the question. So this is the question. So you have token 1, token 2, token n of the question, and then you have the separator symbol. Then, so this is a task where you are given a paragraph, and in the paragraph your answer lies, and you have to tell where the answer begins and ends. Basically, within the paragraph, you have to tell the position of the answer. So what you are going to output is you are going to give the start and end position. So you can use some notation. You can say outside, outside, outside. Suppose begin paragraph, inside, 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 and then outside, outside, outside. So you can say this is the part of the paragraph where the answer is. Okay. So from the separator symbol onwards, this part, you look at the output and you use some notation to label the starting and ending position of the answer.
Ma'am, here the answer can be a word or a sentence also, right?
The answer can be a portion of the text. Basically, you have a paragraph. This is your paragraph. And then you can say your answer begins from here and ends from there. Ends here. Okay.
Yes, ma'am.
And you label that. Another example is named entity tagging, where the input is a single sentence and you want to say this is the name of a person, right? So you say, and there is some notation. Suppose you say Kaustubh Mittal. So you say that Kaustubh Mittal went to Delhi during the vacation. So we say Kaustubh Mittal, we can say begin of person. And then we can say inside, that means Kaustubh is beginning of person, Mittal is inside, went is outside, to is outside, Delhi is beginning of location, then full stop. So this is a notation. So for every word, every word position other than the first position, we can output the class. Another example, this is from an NLI or natural language inference. You have two sentences and you have to output the class of the sentence. So the first sentence can be a premise and determine whether a hypothesis is true or false or unknown. So you want to know that from sentence 1, if it is the premise, is sentence 2 is correct. So whether the hypothesis, so whether sentence 1 entails sentence 2, whether what is said by sentence 2, if I say Kaustav Mittal went to Delhi during the vacation, and we say that Kaustav went to Delhi. So the first sentence entails the second sentence. So this is a relationship, and we want to understand between these two sentences what relationship exists. We have a set of relationship. So here we can get the class as the output. We can have CLS, sentence 1, separator, sentence 2, and we can use the first position to give the classification of the relation between the sentences. Is it okay?
Yes, ma'am.
And then there are various tasks in NLP which requires two text. One is textual entailment, as we have said. Similarly, question paraphrase detection, question answering pair classification, semantic textual similarity, multiple choice question answering. All of them can be encoded in BERT. I'm sorry, I've spoken a lot without a break, so my voice is breaking. So these are some parameters of two versions of BERT, BERT base and BERT large, and you can read them. More details about the model. Is it okay?
Yes, ma'am.
Please read this, it contains some information. This last line is very informative. So both for BERT and models similar to BERT and models similar to GPT and others, big companies with lot of data, lot of computing power, they came up with bigger and bigger models, even containing billion parameters, billion parameters, which were really, really powerful models. And, basically it appeared that, larger the model, the better that it will do. Larger the model trained on, the larger the text, it performed very well. You can get BERT. There are different versions of BERT, Robata, XLNet, etc., which are improvements to BERT. And I will not go through that, but BERT was the starting point. There are modern models which are based on this transformer architecture, but they are more efficient, have less connections, and so on. BERT is useful for many languages, but BERT cannot be intuitively used, though you can tweak BERT to do it for any application which requires to generate text. For example, machine translation or summarization. BERT is not very good. Masked language models are very good at analysis tasks. But for generation tasks, it is better to use unidirectional language model. And GPT is a model which is unidirectional. This is just elaboration of what I said. Bigger models are better. So these are two different tasks. The blue one is a multilingual natural language inference task, and this is another task, which we show that as the number of parameters in the transformer increases, as you have a bigger model, the accuracy is increasing. So it shows that even if we can get even bigger model, you can still get even better accuracy. So before I stop, I'm sorry, we are almost near the end of the class. I just want to introduce GPT in one or two slides. GPT is similar to BERT, but it is one directional. So that it can help in generation. And GPT was, the model was pre-trained model was developed by OpenAI, and there are different versions of GPT, GPT-2, 3, 4, etc., or 3, which the subsequent models are larger. So this is an example, very well-known example of a text generated by GPT-2. So GPT-2 was given this paragraph as input, and it was applied on the, GPT-2 was applied, and the output, you get a story. And the GPT-2 model, if you wish, it is available in the online. You can give a piece of text, and you can watch it generate words one at a time, and you can see how powerful the model is. Okay. So GPT is similar to the, as I said, to the decoder portion of transformer, right? So from the this token, you can try to generate the next word, then the next word, then the next word. So it is one directional transformer. So with this, I will stop today. If we have some questions, we can discuss.
Ma'am, are you going to discuss Groper model in the next week?
What is the model?
Groper, ma'am.
I don't know. First of all, I will not be taking the class next week. In fact, there is no class next week. But if you have some queries, later next week I'll be out, and because on 6th there is no class, and 7th your test is there. But I did not follow what is the model. Can you write it in the text box? So can you write what model you are referring to?
I wrote, ma'am. Can you see?
That's a Gopher. Now Gopher is model for what? Gopher that I knew earlier was different. This thing. I don't know what you mean by Gopher model.
Like I was recently reading an article on Google.
I studied Gopher in the context of information retrieval. For
like language transformation Google made, ma'am. Yesterday I was reading an article, 280 billion parameters Gopher model for language transformation.
Maybe, as I said, there's an arms race going on, and this was the first this thing. I will not teach, but you can go through that. What we have done in this course, we have talked about the essentials of these architectures. I have not come across the model. I have looked at the other models, but these have different tricks. So I think you can go through the paper, and then if you have any questions, then we can have a look. Basically, the new models, I have not looked at Gopher model. Basically, the newer models are larger, have more parameters, plus they try to make the system more efficient in a transformer self-attention, from one layer to another layer, there are order n square computations, right? So most of the later, the modifications to the transformer model, they try to do several things like permutations and other things. They also try to make sure that the next level, you do not look at the entire sequence, but only parts of the sequence according to some well-generated patterns, so that overall you can look at the entire sequence, but you can make it this way. So, that sort of thing I'm aware of. I'm not sure about the Gopher model. I'm sure it has several billions of parameters.
It was better than, say, like it has better results than GPT-3. That's why I was reading it.
So as I said, Gopher and GPT or BERT. BERT is the starting point. There are many transformer models. And these models have two components, mostly the ones that I've studied. One is they have larger number of layers. They are trained on larger corpus. Secondly, there are some efficiencies brought in by making the connections sparse. In self-attention, the connections are dense. They make the connections sparse. This specific model I have not studied, but I think there are many such models, and this may be the latest model. And what I understand is the model gets the power from their size.
Okay, ma'am. And what about exam date, ma'am? We didn't receive anything.
The exam date is on 7th.
Ma'am, will we have any before quiz and anything next week?
Yes, actually, the quiz is supposed to be on 6th. The TAs and Devdut will correspond with you because they are coordinating the course, right? 6th, unfortunately, there is no class because the classes have been suspended, but the quiz or assignments, whatever is remaining, that will be conducted on 6th. Otherwise, the mail will be sent to you and the exam will be on 7th. The final class test will be on 7th.
Hello, ma'am.
And the details will be there in the course website. I'm told that the course website has the details of all the questions.
Hello, ma'am.
Yeah.
Our assignment is done. 2 assignment is done, but can you only conduct in the only final exam before any no quiz before 7, because
No,
our others
that
exam are
will be-
going on every week.
I understand, but we have certain certain things that we have to fulfill. So I will not be able to answer today. So the details will be available on the website. Please look at the class website. I wanted to give an assignment from the RNN part, at least a hands-on, but I will not be giving. From this part, there will be no assignment, but hopefully you can learn on your own when you want to. But about the other quiz, etc., please check the class website.
Ma'am, what type of questions from last 4 lectures in final sim? Final MCQ or descriptive type?
We will have questions which will require you to understand whatever has been taught, and the final answers may be objective, but it is not just that you have to take. You have to work out the answers, and then maybe the answer is objective.
Okay.
Ma'am, I have one question.
Yes.
But it is.
Yes, what is your question? Sorry, I could not hear your question.
I think he got cut.
Did someone remove him?
No, he's still there, but I think some issue with his connection.
So let me wait. Hopefully his connection will come back. Anybody else has some questions?
Ma'am, one question. If I take word for sentiment classification, right? Let's say I'm doing a sentiment classification. Okay, and so if I use BERT for this, ideally I should be getting the weights. Let's assume there are only 3 classes as of now: positive, negative, and neutral.
Right.
Okay, so if I use BERT for this, ideally I will be able to repurpose the weights and the layers from the BERT rather than me going through the entire process, right?
Yes.
So what I want to understand is, ma'am, in a neural network, the weights and bias are dependent on the dependent variable, right? So for example, today, my output classes, instead of 3, positive, negative, and neutral, let's say I'm getting 5 classes: highly positive, mildly positive, neutral, etc. My weights and bias will obviously change. So how will I be able to repurpose those same weights and biases?
No, I have a BERT model which has this million, billion, whatever parameters. And at the output, we have CLS, we have these outputs. Okay.
Okay.
We have a BERT model with the parameters. Parameters are there. They have been pre-trained. Now we have 1,000 examples of sentences and their classes. Right?
Correct.
Suppose at CLS we have a vector. And just suppose that original vector is a 100-dimensional vector.
Okay.
Okay. Now from this 100-dimensional vector, I want to get 3 classes.
Correct.
So I have a linear layer which takes the 1,000 as input and
Correct.
3 as the next layer.
Correct.
So we have this 1,000 into 3,000 new weights.
Correct.
And new parameters. These parameters are not there in BERT.
Correct. Correct.
And then we have a softmax on top of it. Now, when we fine tune, we learn all these new parameters with 3,000 new parameters. Sorry, 300 new parameters.
Correct.
As well as I can fine tune the parameters of the BERT if I wish.
Okay.
Okay. So to go from the output of BERT to your desired answer, so at CLS, we may have a 100-dimensional or 768-dimensional vector. But your task may be a binary classification, maybe a 5-class classification, maybe a 20-class classification. Accordingly, you can have a simple linear layer. You can have any function which takes you from the original vector that is there at CLS to your desired format. Is it clear? Suppose your output is a numerical value. Suppose it is the sentiment score, polarity score between 0 and 1. So you can go from the 768-dimensional output via a linear condition. And these new parameters you have to.
Okay.
Hello, ma'am.
Yes.
Ma'am, actually, I have a kind of a general question. I have a computer vision problem, but I need to find the spatial proximity of one class with respect to another class. Okay, and then based on the the spatial relationship between 2 classes, I need to take certain decisions. So there are multiple approaches. One is like I can use a normal CNN-based classification and classify individual classes, and then maybe can find
I did not understand spatial classification. Can you explain?
a spatial proximity between 2 different classes. For example, whether one class is near to another class, or one object is near to another
Spatial
object.
means semantic semantic.
No. Spatial means the say the distance. For
Can
example.
you give an example?
Say for example, I have 2 classes. One is say a tree, and another one is could be say a water body, say from basically from a satellite classification point of view. I have a water body and a tree.
You want to say the object tree is close to the object water body
Yeah.
in this picture. In this picture.
Close to the water body. Yeah. Yes. So I have multiple approaches here. One is I will separately classify water body as well as tree, and I will find out the spatial. I mean, I can find out the distance between a tree and water body. Yeah, and based on that, I can take certain decisions. And the second approach is I can create training samples.
Okay, please.
Yes, ma'am. And the second approach is like I can create a set of training samples having the similar distributions of trees and water bodies, and create a classification based on this distribution.
You know,
So
I do not know the details, but for me, if you can find out the positions, you can do a simple, Euclidean distance. That would be the simplest thing to do. Don't use a neural network where you don't need to use a neural network.
The neural network I can use for classification of these objects.
I have another meeting, so can you please ask, send me the question?
Sure, ma'am. Sure.
On email. Okay.
Sure.
I will leave